just learned how to find the work done by a variable force. Now, the spring force is a variable force, which means that the actual spring force changes according to the displacement of the spring, whatever displacement it has from its equilibrium position. So we're going to talk about first what the spring force is, how to find the spring force, and then we'll actually derive the work equation from the variable force work equation that we learned before. So springs, we know, have a relaxed state that we call equilibrium. And in that relaxed state, we say that our position from equilibrium equals 0 and the spring force is equal to 0, because that's like the state that it wants to be in. When there's no forces involved, that spring is at its relaxed equilibrium state. So if we then pull that spring or compress that spring, there is a restoring force that wants to restore the spring back to its equilibrium position, and we call this the spring force. So we can see here, this is the spring's equilibrium position. If this person pulls that block back, thus stretching the spring, we have a certain X position from equilibrium. Or if we compress this spring here, this is the position from equilibrium. So we can see that the force is a restoring force, meaning it's in the opposite direction of the displacement because it wants to restore this spring back to its equilibrium position. And here again, it's opposite that displacement because it wants to restore the spring back to its equilibrium position. So the equation that we get for the spring force is negative kd, or negative kx, you will see as well. This is called Hooke's law. So this equation right here, it has a negative in it, and that indicates the direction of the spring force. So we know that the spring force is always going to be opposite the direction of displacement d. So again, if we look at this figure right here, if we have a positive displacement, the force will be in the negative direction. If we have a negative displacement, the force will be in the positive direction. So that's why we have a negative in that equation. Now, a lot of the time when I'm putting the spring force into like a Newton's second law problem and I draw it in my free body diagram, we are giving the direction of the force with our arrow. So I will drop the negative a lot of the time and then just put like absolute value of the displacement in my equation. So that negative is just reminding you that this is a restoring force, okay? Force and displacement are always going to be opposite with the spring force. So K is what we call the spring constant, which is a measure of the stiffness of the spring. The higher the K value, the stiffer the spring. And you'll see values ranging from like 20 to 8,000. So if you see a spring constant K value in the thousands, do not be alarmed, okay? The unit for K is newtons per meter. Like I said, large K, stiffer spring, and the units are newtons per meter. And then, of course, that D is the displacement from equilibrium. And sometimes you'll see X instead of D, same thing. So the spring force, like I said, is a variable force, meaning it's always changing. And again, we know that force is equal to negative kx or negative kd. So that means that this force depends on how far we are from equilibrium, which is why this is a variable force. So therefore, we can't use the work equation we used before, because remember, work is equal to force times displacement times the cosine of theta. That's only for constant forces. So this is not a constant force. It depends on the displacement from equilibrium. The larger the displacement, the larger the spring force will be. So instead, we have to break up the displacement into that infinitesimal segments and add them up by integration. So we're just going to integrate this force with respect to position in order to find an equation for the work done by the spring force. So let's derive that. We know that work is equal to the integral of force as it changes with displacement. So here we know that the spring force is equal to negative kx. So we're going to put that in for the force equation, and we get work is equal to the integral from x initial to x final of negative kx dx. So that means as it changes with x, with respect to x, I mean. So this k right here and the negative, those are both constants, so I can factor that out. And then we're just going to be taking the integral of x. So remember, when we take the integral, we add 1 to the exponent and then divide by that number. So the exponent is an imaginary 1. I'm going to add 1 to that, so 2, and then I'm going to divide the number in front of x by 2. So 1 divided by 2. So we end up getting negative k, which was our constant out here, times 1/2 x squared, and then we're taking this from x initial to x final. Oh my gosh, I'm sorry, Ronnie's barking. You can see him right here. So remember, when we do this, we're going to plug in x final first and then subtract that, plug in x initial. So it's always final minus initial. So we end up getting negative k times 1/2 x final squared minus a negative k times 1/2 x initial squared. Now, because we have minus and negative, this ends up being a positive. So I'm going to rearrange this so that our positive is in the front, and we end up getting that the work done by the spring force is equal to 1/2 kx initial squared minus 1/2 kx final squared. So this is our equation for the work done by the spring force. Now, it's an interesting equation because it looks very familiar, right? It looks like the work energy theorem, and that 1/2 kx squared, we know that is our potential energy, our elastic potential energy equation. So you have to be very, very careful with this because you guys are used to using your final minus initial all the time, but we have to note that x final is in the second part in this equation. So it's initial minus final. All right, so be very careful about this when you use this equation. Now, what this tells us is that the work done by the spring force is going to be positive if the block ends closer to the equilibrium position than it was initially, okay? And it's negative if it ends farther away from the equilibrium position. So, work done by an applied force. If we displace a block along the x-axis by applying a force applied to it, both the applied force and the spring force do work on the block. So here's our spring force here. Our applied force in this case would be in this direction, the opposite direction of the spring force. Our applied force in this case would be in to the left, which is again the opposite of the spring force. So using our work kinetic energy theorem here, we can get that the total work or net work done on the object would be the work done by the applied force plus the work done by the spring force, and that's going to be equal to our change in kinetic energy. Now, if we don't have a change in kinetic energy, so our final kinetic energy equals our initial kinetic energy, then our work done by the applied force will equal the negative work done by the spring force.